Okay, thank you very much. So this is a joint work with York, and so many people gave a talk in project the slide, and I'm from Japan, which is supposed to be a technologically advanced country, but I use this old-fashioned technology. So in this talk, set of alphabet is 2-point set, arbitrary 2-point sets. And so I think many of us are familiar with the concept of substitution. So this is the map. So that's a map of domain A, and this A star is a set of all finite words. So this is such a map. Arbitrary map is for the substitution map, the binary substitution. For example, so I think many of us are familiar, but that's the example. Kushi, 2 emos, and 1, 2, 1, 2, and this kind of substitution. 2 emos substitution. And so to each substitution, there corresponds a matrix. It is defined by this equation. So Aij is a number of I in Cauchy. So I and j are 1 or 2. So for 2 emos, the substitution matrix is 1, 1, 1, 1, and for Fibonacci, substitution matrix is and today I want to mix several substitutions to generate a word, which is called the S-adic word. So that's a sequence. So arbitrary sequence of binary substitution is called the directive sequence. And given directive sequence, we can always generate an infinite word, which is something like this. So we want by infinite was something like this. Like this. So let's explain. A word of this form is called the S-adic word. So this is a dot is a place of origin. So probably if we start with 0.1, then we can, for example, apply row F to get 1. We are not using 0 and 1. So 1, 2. So 1, 2. Next step, we have this. Then we can apply arbitrary substitution. So, for example, we can apply 2 emos, then this becomes something like this, and so on. So, we can apply substitution by this order. So given objective figures, we can apply this. So the INJ is some letters. And if we choose nice IN, and JN, then this is convergent. Maybe we can take a subsequence of AN. So because this second word includes the first word. So for example, we can apply row FTM, row F, CF, CTM again, then the words gets longer and longer. And with respect to the product topology, it converges to some bi-infinite word. And so such bi-infinite word is S-adic word. So I think this is not very much new to this audience. So, but I'm not sure we are very much familiar with tiling, so we discuss it. So let's start with the bi-infinite word. And so some tile lengths L1, L2. So let's denote this. Like this. I don't know, this is not the set. So given a word, and we have to specify tile length, which is L1 and L2. Then we can get tiling. So something like this. So this is, so let's denote T1 is the interval of this. And we can juxtapose T1 and copies of T1 and T2 by the order of this infinite word. So this is the origin, then this is TA0, and this is, so this is a translate of TI1, and this is translate of TA2, and this is translate of like this. So such a infinite family of tiles is called the tiling. So in this tiling is a set of intervals, and such that intervals have empty interior intersection, and they all together cover the whole real line. So such family of intervals are called tiling in one dimension. And given a word, so we want to discuss tiling dynamical systems. So given word, so this is symbolic settings. First discuss symbolic setting, then we consider all the shifts and take closure with respect to the product topology. So this sigma is a shift, and this is called this is the half for the word. So this is symbolic setting, and there's a geometric analog. See? And given a tiling, and we consider all the translates. With respect to certain topology, so to take closure with respect to certain topology, which is similar to the product topology here. So we will discuss what this topology is, but we take orbit and take closure. And this is called continuous curve. So the topology is defined by a metric. So two tilings, the distance of two tilings are close if this is the definition of metric. I think first 20 minutes is just definitions. And we start to talk about the result later. So the metric law is less than epsilon if there exists a small real number is absolute value less than epsilon. So this b epsilon is more around the origin. If the small vector such as translate agree inside this large ball, so this is the origin center and radius 1 over epsilon. Then if they agree in a large region after small translation, then we say these two tilings are close. So let's discuss example. So this is so let's start with so this just the simplest tiling of unit intervals. And if we consider translation, and if we translate one to the right, we come back to the original tiling. So if this is T1, then T1 plus 1 is T1. So shift everything by 1, then we get the original tiling. So the orbit of this tiling is unit circle, or something like this. And let's consider another tiling. So similar tiling, but there is 0-2 interval at the center. And this is not translation invariant. But if we translate Tn by n, T2 by n for large n, then around the origin, T2 plus n is the same as T1, if n is large. So T2 plus n goes to T1, something like this. Okay. So with respect to this matrix, two tilings are close if they agree in a large region around the origin after small translation. So, but without translation, these two tilings are close around the origin. So we can even add n1 over n here to have the same convergence. So this is the orbit of T1, the orbit of T2 wind closer and closer to this orbit of T1. This is orbit of the red half is orbit of T2, and this is orbit of T1. Right. So, this is and if we take union of these two orbits, then we get the half of T2. So this is the image. continuous hull for T2 consists of two orbits. And we have running out of time, but okay. So often, what? So T is a tiling in R, and R acts on this hull. So this XT is continuous hull is a set of tiling. So given S from XT and some real number, we get we can consider its translation. Then its shift S plus X is again in XT. We can prove this. So, and this is a continuous group action. Then often there's unique invariant probability measure mu. Often, I think in this talk, there's always invariant probability measure mu. And so this is probability measure, so they correspond to L2 space. And Koopman operator is defined by this. So whenever we pick X in R, we get shift action of by vector X. Okay. And then we can define the pure spectral property of this family of unitary operator UX. So T has here point dynamical if so this is just an operator, UX operator. So we can consider eigenfunction and eigenvalue and eigenvectors. But in this case, eigenvectors are functions. So we call them eigenfunctions. And if there are many eigenfunctions, many eigenfunctions F1, F2, and if they form a complete orthonormal system for this L2 space, we say the tiling has pure point dynamical spectrum. So this Fn is eigenfunction simultaneously for all Ux. So Ux, there are many Ux. So X runs through the real line. So many Ux, many operators. And Fn is simultaneously eigenfunction for every operator. And there's a theorem. So why this is interesting? Theorem. This pure point spectrum is characterized in the following conditions. So the first condition, this is the following equivalent. And the first condition is T as pure point spectrum. Second condition is T is mean almost periodic. And third condition. So he has pure point spectrum. The first condition is pure point spectrum, which we define now. And the first condition is essentially the diagonalizability for unitary operators UX. And the second condition is mean almost periodicity. He has pure point spectrum if and only if he is almost periodicity in a sense. So this is studied by Guede and later by Lenz, Spindler, and Strungaru. And pure point spectrum is equivalent to almost periodicity. So almost periodicity is a kind of weak symmetry. So we have tiling. Then if we shift, they never coincide unless the tiling is periodic. But sometimes for nice shift by nice vector, the shifted tiling coincides with the original tiling. Almost coincides with the original tiling. And that's a condition of almost periodicity. So this is a kind of weak symmetry. And the third condition is this group action is conjugate to a rotation on a compact abelian group. So this pure point spectrum, the system with pure point spectrum is classified by its eigenvalues. So in particular, this if it's pure point spectrum, it's conjugate to a group rotation. But the compact abelian group is not necessarily a torus. So the third condition is a classification condition. So we want to know when a tiling has pure point spectra. So this conjugate to a rotation condition is proved by a similar method for Z action. But this is R action, so but a little bit different. We need a little bit of operator algebra. And the theorem by Hollander Solomia single substitution. And then this XW what a Pisot condition. So we forgot the Pisot condition. So the Hollander Solomia proves that sequence of walls generated by a single substitution, and if it satisfies a Pisot condition, then the corresponding dynamical system is pure point spectrum. So this is So this is only for binary. So if this not necessarily binary, it's a Pisot conjecture. So they set a Pisot condition for binary case, but this is only for single substitution case. Okay. And there's a theorem by many people here. So there's a we have 4 or 3 minutes? 4 minutes. Okay. So assume Cn is unimodular. And what is this is observed. So this is multiple substitution case. And they assume each Cn is unimodular, which means the substitution matrix has determinant plus or minus 1. And they also assume that recurrence property for directive sequence. So for arbitrary natural number L, there corresponds a large n such that this sequence, the part of a sequence coincide. There's a recurrence property for the directive sequence. And then they prove that the S-adic word, so W is a S-adic word belonging to this directive sequence, and we take a hull, which is a compact space, and shift action acts on this space, and this is conjugate to conjugate to a rotation on S1. This is proved by Valerie and others, York and Milton and Wolfgang. And today we claim this. So let's pick 2 by 2 irreducible primitive. Pisot. And what is this? So this is the directive sequence. Such that AN is so we consider a situation where matrix is almost fixed. So we assume there is 2 by 2 irreducible primitive matrix is non-negative integer entries, and assume the Pisot Heron-Frobenius eigenvalue. We take a directive sequence, And we assume that the substitution matrix is power of this n, all power of this n. Then we have S-adic equals and we get suspension tiling T by choosing appropriate tile length. So tile length is not arbitrary right now, but we can take appropriate tile length, the T, then we can say this XT is pair point spectra. So the point is we don't assume unimodularity, but this is weaker than this theorem in the sense that matrix is almost fixed. So matrix power of the fixed matrix. Which one? Oh, yeah. Sorry, I forgot that we assume Pisot condition. So we have sequence matrix. Then, so in one direction it's expanding, and in another direction it's contracting. Yeah. Binary, yes. So the index of everything is binary. Yeah. Yeah, okay.
Thank you very much.